We will now discuss relation between modulus of rigidity G and modulus of elasticity E. Modulus of rigidity is equal to modulus of elasticity E divided by 2 small bracket 1 plus nu, where nu is the Poisson ratio. Before getting into the skin of this relation, we will first discuss generalized Hooke's law. If a material at a point is subjected to a state of a triaxial stress, i.e., sigma x, sigma y, and sigma z, these stresses will produce associated normal strains, that is, epsilon x, epsilon y, and epsilon z. We know from our previous knowledge that the stresses can be related to strains by means of Hooke's law. If we consider stress only in one direction, then Hooke's law can be applied in isolation to relate the stresses with strains. However, in the case of a triaxial stress state, what we are discussing now, the stresses can be related to strains by using Poisson ratio and Hooke's law. The Poisson ratio and Hooke's law are applied by using the principle of superposition. The Poisson ratio, which is denoted by nu, is a measure of relative deformation that occurs when a material is subjected to stresses. It describes the ratio of transverse strain to axial strain when material is stretched or compressed. If a material is stretched or compressed in one direction, then the Poisson ratio will indicate how much it will contract or expand in perpendicular directions. Thus, the Poisson ratio is actually the ratio between the lateral strain and the longitudinal strain. In other words, it is a ratio between transverse strain and axial strain. The reason we are having negative in this ratio is because the nature of transverse strain and axial strain is different. Like, for example, if we have a stretching in one direction, then due to Poisson effect, there will be compression in the transverse direction. In this 3D cube, stress is applied in the x direction. So the strain in the same x direction can be written as equal to sigma x by E. Due to this stretching strain, there will be compression developed in both the transverse directions. The strains in the transverse directions can be determined using Poisson ratio. The application of sigma y on this 3D element will produce contraction in the x direction. Contracted strain epsilon x double prime can be written equal to minus nu sigma y by E. Sigma y by E is the axial strain in the y direction. So this expression is actually relating the contracted strain in x direction when we have stress applied in the y direction. In a similar manner, the stress in the z direction will cause contraction in the x direction. So using the Poisson ratio expression, we will get epsilon x triple prime equal to minus nu sigma z by E. After this, we can use principle of superposition to add all the strains in the x directions. So epsilon x bar, which is due to the axial stress, epsilon x bar bar, which is due to the stress in the y direction, and epsilon x triple bar, which is due to the stress in z direction. Thus, epsilon x will be equal to 1 by E big bracket sigma x minus nu small bracket sigma y plus sigma z small bracket close and big bracket close. In a similar manner, we can derive the strain expression in y direction equal to 1 by E big bracket open sigma y minus nu small bracket open sigma x plus sigma z small bracket close big bracket close, and epsilon z equal to 1 by E big bracket open sigma z minus nu small bracket open sigma x plus sigma y small bracket close big bracket close. In the case of biaxial stress, we will have sigma z equal to 0 and also epsilon z equal to 0. Thus, epsilon x will be equal to sigma x by E minus nu sigma y by E, and epsilon y will be equal to sigma y by E minus nu sigma x by E. Now, these two biaxial strain cases will help us to derive the relation between modulus of rigidity and modulus of elasticity. Let us assume a biaxial stress state having tensile stress sigma x in the x direction and compression stress sigma y in the y direction. Both the stresses, i.e., sigma x and sigma y, are equal in magnitude. Using this stress state, we can draw a Mohr circle whose radius would be equal to either sigma x or sigma y. The Mohr circle also shows that we would have a pure shear state equal to sigma x or sigma y. In other words, our principal shears plane, we won't have any contribution from axial strains. It is because of this reason that we assume the stress state shown in the figure A. Thus, the stress state in figure A is of pure axial strain, whereas at 45 degree we have pure shear strain. This pure shear state is shown by the box A, B, C, D. Due to the pure shear, diagonal BD will be compressed to B prime D prime, and diagonal CA will be stretched to C prime A prime. The deformed element due to pure shear is shown by dotted lines. Before deformation, the angle between the concurrent line of this box is 90 degree. In other words, the angle between BC and CD is 90 degree. Similarly, CD and DA is 90 degree. DA and BA is 90 degree, and the angle between BC and BA is 90 degree. After deformation, the dashed profile shows that the angle between A prime D prime and A prime B prime has reduced from 90 degree. Similarly, the angle C prime B prime and C prime D prime has decreased from 90 degree. The angle between B prime C prime and B prime A prime has increased from 90 degree. Similarly, the angle d prime c prime and d prime a prime has also increased. We can say that the right angle at A has decreased to 90 degree minus gamma, where the right angle at B has increased to 90 degree plus gamma. Gamma is the shearing strain. Since sigma x is equal to minus sigma y is equal to tau, we can put the values in the biaxial strain expressions, and we will get epsilon x equal to tau small bracket 1 plus nu by e. Similarly, epsilon y will be equal to minus tau small bracket 1 plus nu over e. The deformed lengths of the sides OA and OB can be written as OA bar is equal to OA big bracket open 1 plus tau small bracket open 1 plus nu small bracket close divided by E big bracket close. Similarly, OB prime will be equal to OB big bracket open 1 minus tau small bracket open 1 plus nu small bracket close divided by E big bracket close. We can also look into these expressions since OA prime is equal to OA plus this plus the difference AA prime, and AA prime will be equal to the strain in X times the original length OA. Hence, we have got the expression OA prime shown over here. Similarly, OB prime will be equal to OB minus BB prime. BB prime will be equal to the strain in y direction times the original length, which is OB. Right triangle OA prime B prime will be equal to tangent 45 minus gamma by 2, and which in turn will be equal to OB prime by OA prime. Hence, we have written tangent OA prime B prime is equal to tangent 45 minus gamma by 2 is equal to OB prime by OA prime. And plugging the values of OB prime and OA prime, we will get 1 minus tau small bracket open 1 plus nu small bracket close by E divided by 1 plus tau small bracket open 1 plus nu small bracket close by E. Tangent 45 minus gamma by 2 can be expanded in a trigonometric form as tangent 45 degree minus tangent gamma by 2 divided by 1 plus tangent 45 degree tangent gamma by 2. Since tangent 45 is 1, tangent gamma by 2 can be approximately taken as gamma by 2 again divided by 1 plus tangent 45 is 1 and tangent gamma by 2 can be approximated as gamma by 2 since gamma is considered small. Thus, we can write 1 minus gamma by 2 divided by 1 plus gamma by 2 equal to the expression 1 minus tau 1 plus nu by E divided by 1 plus tau 1 plus nu by E. After carrying out some algebra, we will get gamma equal to 2 tau small bracket open 1 plus nu small bracket close divided by E, or tau by gamma equal to E by 2 small bracket open 1 plus nu small bracket close. Tau by gamma is equal to G. Hence, we will get G is equal to E by 2 small bracket open 1 plus nu small bracket close, which is the desired relation between G, E, and nu.